So, good afternoon, everyone. Please ask your queries about the course. Course deals with basics of quantum mechanics in terms of the linear vector spaces, expectation values, um, operators, Hilbert spaces, and all that. And then the course goes on to some of the application aspects that are needed for any branch of physics. And some of them are, for example, perturbation theory, etc. And then I've also introduced the basics of quantum computation and various other things. And in that context, or even, I mean, which is also relevant for optics, there are this concept of these entangled states, etc., which I have used in this teleportation, quantum teleportation. So these are the things, and then finally there was some scattering theory that was developed. So every problem in quantum mechanics or even in classical mechanics is it's a supposed to be a scattering problem, but you have to understand that in classical mechanics, scattering is very different than that is in quantum mechanics. In classical mechanics, any particle with any momentum energy, say E and K, can scatter into any of the states, E prime and K prime, and there's no restriction on that. In quantum mechanics, that is important because you need to have the states empty for the particle to scatter, especially if the particles are fermions or electrons. So that's where a lot of interesting things come. And as in any scattering problem, the main objective is to find the scattering cross section. So, and this scattering cross section would crucially depend upon um, the selection rules and so on. We particularly use what's called as a Born approximation to calculate the scattering cross section. Okay, and then there are things such as partial waves, etc. We also, as part of the approximate methods, we also do variational calculation, where you may not assume that the solution for the unperturbed problem is available. So you can take a variational wave function with hopefully with one variational parameter. Sometimes that's not possible. We have, of course, restricted ourselves with one variational parameter, and um, and then you minimize the energy with respect to that parameter and put it back into the wave function. And that wave function gives you the upper bound on the ground state energy. It's not only about the ground state energy, you can get any excited state energy as well. So that's about the variational calculation. And there are examples where we actually don't know the solution of even the unperturbed problem, so, which is mostly the case. And one of the very famous application of the variational calculation is what is known as the BCS theory, which is called as the Berding-Cooper-Schrieffer theory for superconductivity. So, and we have also done what's called as a WKB approximation, Wenzel, Kremers, and Brillouin, which tells you that for a constant potential, it doesn't matter whether you match the wave functions from left to right or right to left; they will always be same. But there are certain situations in which, if you try to match the wave functions in the wrong directions, you'll end up with difficulty. So that's about the this WKV approximation. In fact, WKV approximation is also very helpful in solving problems for which exact solution doesn't exist, because it gives you a condition when the canonical momentum integrated over the entire canonical coordinates of all canonical coordinates, it gives you a constant. And if you use this, then you simply have to identify the canonical momentum and the canonical coordinates. That's in very brief the upshot of the course. If you have any questions, I'll be happy to answer. There was one question about, I couldn't actually get it. It said that while calculating the expectation value of the operator, if ion is watching, then I've used a delta function. You have to just say that in what situation. And about the maximally and the minimally entangled state, what I mean to say is that a state that cannot be split into two states, such a single particle state. So you take two single particle states and you combine them in a manner that you cannot separate it, extricate one from another. That's called as an entangled state. And suppose you say that there are various degrees of inextrication. That is, one cannot be really taken out from the other completely. So that's called maximally entangled state. And if there are partial overlap with the states, so actually we have not talked about anything other than the maximally entangled state. So if there are questions, I'll be happy to answer. Yes, good evening, Vikas. Please go ahead. So let me take Vikas's question. Um, so n and theta are it's a little difficult to understand. But if you think that one of them is related to energy and the other is related to time, then you can use uncertainty relation. In especially, this is to answer Vikas's question. This is actually with regard to superfluidity, where one actually talks about the number of particles with the twist in the superfluid order parameter. So there is a delta n delta theta which exactly uses the same the uncertainty relation as you get it for the delta P and delta X. Okay, so this is if you have not really know how to derive it, it's not a problem because this is very special to superconductivity or superfluidity, but even superconductivity would be there. So it's delta n is the number of the say superfluid pairs or the Cooper pairs, and theta is in that case for superconductors, theta is the phase of the wave function. So these actually have a canonical relation which is similar to P and X. Okay, this if you don't know the how to derive it, that's not a problem. Okay, just know that there's a delta n and delta theta has a relation which is similar to delta P and delta X. And I still don't understand this question because I probably have forgotten where this thing. But please do write to me with a reference for the what exactly you want to know. The delta function property I used while finding the expectation value of the operator with a wave function being a delta function. All right, let me, if I can have the slide. Rekha, can I have the slide? Rekha, can I have the board? Thank you. So what might have happened is that, so if your wave function is like a delta x minus a, then okay, so let me write it again. So your wave function is, for example, a delta x minus a, and then of course some constants could be there which is there to normalize. So if you want the expectation value of some operator, so then you have to get it, you have to write it as, let me, not use this for a while, so I forgot. All right. So let me sort of, so this psi and O and psi. So this is your, I mean, in the sense that, what's happening? Okay. So, so there's a delta x minus a O delta x minus a and dx. So this gives you, so this is like O of x. So it ultimately gives you O at a, the value of the operator at a. I'll not write it. So this is, if I have used something like this, but you could actually write to me in my email address, and then I can reply. You can just refer to the place where you were talking about. I've used from your question, it's not very clear what exactly you want to know. Okay, but I might have used, just as a clue, I might have used a relation which is delta x minus a, x equal to from minus infinity to plus infinity, and dx is equal to f of a. I'm sure this is one of the very usual property of the delta function that everybody uses. So I might have used that. So you just have to help me in locating where I have used this. Okay. So so in this thing, if you have a wave function which goes like a delta function, which is like just a a wave function is a delta function is a sort of slightly difficult thing for me to understand whether I have really told that, because it is usually not a delta function. Okay, it has a functional form in most of the cases. So I might have told something else. That's what my initial hunch is. Can I go back? So, and please write to me with the marker of the video that you're talking about, then I'll be able to answer your question better. If you have other questions, you can ask. Aman, okay. Provided the solution, I will try to at least give you the final answers, if not the whole working steps. So I'll ask the TAs to provide you with the solution after the scores have been displayed. Yes, we can do that. Aman Mishra. I'll ask the TAs to display the final answers as well of the assignments, tutorials. Thank you, Aman. No, that's a good question. I mean, in the sense that the two delta functions actually don't make sense if they refer to the same thing. That's what I meant. I mean, in the sense that if you have two delta functions, you can ignore one, because a delta function inside an integral, whether it is one or two or three, it really doesn't matter, unless they refer to different variables. Okay, here the variable is same, which is x, which is peaking at a space which is a coordinate given by x equal to a, then it doesn't matter whether you have one delta function or more than that. Now, I find it quite difficult to understand why did I use two delta functions, or why did I take the wave function as a delta function. See, what might have happened is that, say, for example, when you want to talk about a charge q, so we write it as q into delta of r, which means that the charge is located at x equal to 0 or r equal to 0, or wherever you want to this thing. And then you want to integrate, suppose you are talking about Gauss's law. We are not talking about the expectation value, but we are trying to calculate Gauss's law. In that case, you actually write this q as a point charge, which is q into delta r, and then you sum over all the area of say, for example, a sphere, in order to get the flux, which is I mean, in the sense that E dot ds is equal to q by epsilon 0. So if you need to calculate the electric field by using this Gauss's law, then you need q to be written as q delta of r. But you really have to show me what you are exactly referring to. It's not fresh in my mind. But when you write to me, I'll definitely reply. It's not clear to me which part, what exactly is the situation in which I actually refer to this. And you really are talking about a function. When we talk about a wave function, this really means that the particle is completely localized at x equal to a, in which case the momentum uncertainty goes to infinity. So this will have difficulty in really specifying it as a wave function just before a position measurement. Okay, you have to give it. So what you can do is that you can write it as exponential minus x minus a whole square divided by some 2 sigma square. Okay, that is a Gaussian, and the Gaussian can be very nicely taken as if the particle is near x equal to a, and you have given it a spread. Okay, so that is quite possible, but writing the wave function just before the position measurement, this is quite unlikely. Is not correct. Uh, Oh, you meant, sorry, yes, yes, yes. See, just after the position measurement, you said after, okay, I sort of, even after the position measurement, because it's a wave, so you have to give it a wave character. Even though the delta function is a function, it is not, because delta x minus a is peaked at x equal to a and doesn't exist anywhere else. So if that is true, then according to this, see, the point is that what I'm trying to say is that if you take psi equal to this and calculate the momentum expectation value, the momentum expectation value will go to infinity. So momentum expectation for a particle going to infinity means that it is not it's a completely unbounded case. I'm not talking about bound particle, but so this is not a real wave function. If you are asking that question, this is not a wave function. It's not allowed by the uncertainty principle. Yes, absolutely. Yes, absolutely correct. That the square integrability will also be violated. And the momentum eigenstate will be a theta function. That's another problem. Okay. But they are all related. You're correct. Yes. I mean, in the sense that your square integrability can be still be validated if because the delta function is a function which blows up, but its integral is finite. So a delta square doesn't make sense, but it still can possibly be, thinking that it's just one delta function. So that way it can be accommodated. But uncertainty principle is main thing. Yeah. Um, Ankita, quantum entanglement considering two spin particles by correlated spins possess 100% probability, anti-correlated one. Once again, I'll have to see this. You please, you can please write to me, and then we can discuss it over email, or even if you have further problems, we can talk on Google Meet, etc. But I have to see. But there are, I mean, in the sense that we have assumed that there is the correlated spins possess 100% probability. But you can also prepare the system in a manner that the anti-correlated the spins will also have some probability. Okay, so this is most likely it's been assumed that that's the case for this thing. Okay, but I will again look at this. If you can just write to me with the video that you're talking about and the time stub at what time such discussions are being made, I can have a look at it. All right. Yes, my email ID you can write. That's my first name Saurabh, Saurabh at the rate iitg.ac.in. A for America, C for Canada, ac.in, and IITG is IIT Guwahati. So, just a moment. Yeah, yeah. Thank you. Yeah, I just said that Ankita before probably you have arrived. So in the sense that when you cannot, suppose you make a state out of two single particle states, okay, which are A up and B down kind of state. That's a single spin state, which spin up particle. So you can make a composite state made up of two spins. Now, you can either make it completely that you cannot extricate the components at all, which we have called it as maximally quantum entangled state. That is, from that composite state, you can never get back the individual single spin states. Okay, so that's called as a maximally quantum entanglement state. That state is entangled and you cannot get back. Once that state is prepared, you cannot get back the original states which are A up and B down. Okay, that's called as the entangled state. So there was a question that why is maximally and what if there is a minimal entanglement. We haven't discussed that, and neither it's required for us to discuss. But it just means that if there is a finite probability of getting that, if you make a state in that fashion that there is a finite probability of getting back the individual state, then it's not completely entangled, not maximally entangled. Okay, we haven't talked about such situations because that's not important for us, because what was important is in order to explain quantum teleportation, you need an entangled state of that kind which is completely entangled, and there's no way of getting back uh, anything those individual states. Thank you. Any other question? You have to post your questions. We're running out of time. It's 15-20 minutes remaining. If there are no questions, I'll still wait for 2 to 3 minutes, and then if there are no further questions, then I'll log off. Please post your questions if you have. Please ask your questions because I'll wait for a couple of minutes more. If there are no questions, then I'll log off. Yeah, if you're watching, and then you should be having some questions. I'll wait till 5 o'clock. That's 2 more minutes. Yeah, so why don't we distinguish between states which differ by only by a phase factor? That is because the probability density remains the same for these two states, which has a phase factor or has a different phase factor as compared to the other one. Okay, so that's the mod psi square remains constant, so the probability is stationary. Yeah, so there is this, the action of a rotation operator is like exponential I theta. So it just picks up a phase, but the probability density remains same. Ramon, if that is understandable. Hope that is understandable. For example, a dynamical phase that is exponential minus IET by h cross, that does not give rise to a distinct state because it just evolves the state with time. The probability, so there is a stationary state as it's called. Expression for the rotation operator is not discussed in the. Oh, expression for rotation operator is just, if you rotate something by saying the z-axis, then it's simply, cos theta sin theta 0 minus sin theta cos theta 0 and 0 0 1. That's a rotation about z-axis, but you will find it anywhere if you search for rotation by about an arbitrary axis. You will get it in classical mechanics books. You will all get it. Okay, thank you, Ramon, that you understood the phase factor part. Yeah. So if you write a three-dimensional matrix for the rotation operator, because a psi of r can be rotated by u of r, psi of r, u of theta, sorry, where u is the unitary rotation operator. So that's like cos theta sin theta 0 minus sin theta cos theta 0 and 0 0 1. I've just only considered rotation about the z-axis, but you can do it about any axis. It's not difficult. In fact, in the classical mechanics course, when you talk about rigid body rotation, uh, yes, that's right. So you actually, in classical mechanics, we say rotation matrix, and then you simply multiply it, left multiply it. Here you treat it as an operator and operate on the wave function. Okay, and so that's the only difference there. There you use all these things such as angular momentum, etc. So these are physical quantities in classical mechanics that you consider, and here you consider the wave function in quantum mechanics. Yeah, you just multiply the rotation operator or rotation matrix. Yes. All right. Thank you, Ramon. So there's some questions at the last moment. I'll wait for 1 more minute till 5:05. You can take your. I mean, you can ask me questions, anything, um, and then I'll extend that. It's not that I'm going to stop at 5:05, but if there are no further questions, then only I'll stop. Okay, so I believe there are no more further questions. So thank you for watching, and there'll be a second session coming up sometime, which will keep you informed. And meanwhile, I've already shared my email ID, so you can ask questions, and if you have any difficulty, you can ask questions, and I'll try to, I'll ask the TAs to share the solutions. All right then. Bye bye. Thank you. Stay safe.